990. Once after obtaining this one, then entropy change of the entropy change of the iron cube, entropy change of the iron cube. So that is equal to Mi Cpi ln. The temperatures now, it is 673 divided by 273. You will get the answer here as 2697.8 joule per Kelvin. It is joule per Kelvin. Joule per Kelvin. So here, initially taking this one as 673, taking the 0 degree centigrade as datum water. So taking 0 degree centigrade as datum. Taking 0 degree centigrade as datum. So that everyone has to observe this particular side. So once this is over, then the entropy change of the water. Entropy change of the water. So mass of the water, specific heat of the water, ln, this is 298 divided by 273 is equal to 3667.8 joule per Kelvin. Joule per Kelvin. Joule per Kelvin. So this is taking the entropy of water. Again, one has to be more careful about this particular case. One has to be more careful about this particular datum value. Once this is over, then here the entropy change of the iron, this is the basis here, entropy change of the iron cube at this is at 673 Kelvin. But entropy change of the iron at 323 Kelvin. Then again it is nothing but equal to, so here connect to this one. So that is, this value is 2990, that is 2990 ln 323 divided by 273 is equal to, you will get here as a 502.8 joule per Kelvin. Again this delta S for the water at 323 Kelvin. So try to understand these two, that is, this is the second phase and this is the first phase, right? So if you work it out for this particular case, you will get this one as 7040.4 joule per Kelvin. Joule per Kelvin. Joule per Kelvin. Right? So these are the first stage and second stages. Right, from 673 to 0 and 323 to 0. So once these things are over, then you have to work it out the entropy change of the iron cube. Change is asked here. So that is what is the entropy change, or what about the entropy change happens when it undergoes from higher temperature to the lower temperature, and in between that one, what are the intermediate temperatures. So try to observe all these particular cases. Once this is over, then the other part, that is the change of the entropy. So change of the entropy changes for the iron. Change of iron cube. Iron cube. So in the first stage, you have got that particular value as two things are there. That is, one is in the second stage you have got as a 502.8 minus 2697.8 is equal to, you will get it as a minus 2195 joule per Kelvin. What is happened here? Heat lost by the iron cube. So it is minus sign. Heat lost by the iron cube. Right? So in the same way, the change of entropy for the water. So here also two stages are there. That is the second stage, that is entropy change. You try to observe that S2 minus S1. Here also S2 minus S1. So this is S2 minus S1. Entropy change of the water. So here the 7040.04 minus 3667.8. You will get this value as 3372.24 joule per Kelvin. Then what about the net entropy change? Net entropy change. Net entropy change. That is equal to, so the entropy change of the iron cube IC plus entropy change of the water. So iron cube, it is minus 2195 plus water, it is 3372.24. So finally it is 1177.24 joule per Kelvin. Then what this is going to indicate, that this net entropy change which is greater than the 0. Net entropy change is greater than 0. Hence the process is irreversible. Hence the process is irreversible because it is greater than 0. It is greater than 0. So this is how you need to solve the problem. So because at the end, is the process reversible? If so, why? Then what happens? So all these things you have to give the answer. For all these things you have to give the answer. So this is one problem. And the next one is, so far it is discussed the changes. Now you have to apply that particular entropy for a process. Right? So, or the cycle, where I can tell it as the cycle. Air at 20 degrees centigrade, here air has a working medium. So far we have worked out for the water. Now air is the working medium at 20 degrees centigrade. Pressure is given, occupies a volume. The air is heated at a constant volume until the pressure P2 is also given, and then cooled at constant pressure back to its original temperature. Calculate the net heat flow from the air, net entropy change, and sketch the process on TS diagram. So observe the diagram and sketches, that is the TS plane. So one thing, that is first one is, it is air is heated at constant volume. So air is heated at constant volume and then cooled at constant pressure. and then cooled at constant pressure. So this is the cooling, that is at constant cooled to C. It is at constant pressure back to the original temperature. That means this one up to this stage. So 2 to 3. And the third one is back to the, that is, it is the cycle is going to reach to the initial state. So that is this one, 3 to 1. So this is the constant volume process, this is the constant pressure process, and this is the constant temperature process. So the entire thing, this is nothing but the cycle. This is nothing but cycle. Now you need to apply one by one for this particular cases. That is the heat transfer, because now in this case what you have to assume, it is V1 is equal to V3. That V1 is equal to V3. It is the constant volume, that is 0.025 meter cube. So in this process, that is come to the process 1 to 2. Next one is process 2 to 3. Next process 3 to 1. Process 3 to 1. So first thing is find out the, because we know that P1 we know, P1 is 1.05 bar. V1 divided by R T1. R T1. So P1 is 1.05 into 10 to the power of 5. Observe the units compatibility here. V1 is 0.025. R for air is 287. And the temperature is 293. So you will get the mass value as 0.0312 kg. 0.0312 kg. So in a process 1 to 2, volume remains constant, that is P1 V1 by T1 is equal to P2 V2 by T2, and in a constant volume process, so V1 is equal to V2. Therefore, you will get the value of T2 here, because the pressure is 1.05 and another pressure is 4.5 bar is given. So you can estimate the T2 value from this one. So that T2 value is 1255.7 Kelvin. Once this is over, then you can estimate the process, that is Q1 to 2, and it is occurring at constant volume MCV T2 minus T1. If you sort it out, M is known, R value is 287, and T2 value is 1255, and T1 is 293. So if you solve this one, you can get it as 21.56 kilojoule. And in the second process, that is the Q2 to 3, it is the constant pressure process. So directly you can apply MCP final minus initial, that is the T3 minus T2, right? And this T3 is nothing but equal to T1. T3 is nothing but equal to T1. So you can get here as minus 30.18 kilojoules, right? And when you apply the third one, that is Q is equal to delta U plus W. Delta U plus W. Q 3 to 1. And because it is an isothermal process, it is equal to 0. It is equal to 0 over here, right? So therefore the total heat transfer, which you can get it as Q1 to 2 plus Q2 to 3 plus Q 3 to 1 plus Q 3 to 1, right? Try to work it out and you will get the answer for this one is minus 8.62 kilojoules. 62 kilojoules. So whatever the basic fundamentals you have learned, what about the heat transfer and work transfer in this case? So heat transfer, work transfer and entropy change. So here also heat transfer, work transfer and entropy. Here also work transfer, heat transfer and entropy. So when you work it out, when you work onto this particular side, so that is the first bit. So that is the only first bit, that is the net heat flow from the air. So Q1 to 2, Q2 to 3 and Q3 to 1, you will get the answer as minus 8.62. Then what about the second bit? So entropy change in the process 1 to 2, entropy change in the process 2 to 3, and again entropy change in the process 3 to 1. Then what about the total entropy change? What about the total entropy change? So that one has to work it out. So come to the entropy change. The entropy change here, S1 minus S2 is equal to, it can be written as S2 minus S3 minus S2 minus S1, right? So S2 minus S3, first you come to this one. First come to the, that is S2 minus S3. S2 minus S3, where the formula which you are going to be getting as, it is the constant pressure process, which is going to be coming in between 293 to 1255 mCp dt by T. So when you sort it out, this one, you will get the answer as 0.0456 kilojoule per Kelvin. The second case, that is S2 minus S1. S2 minus S1, that is, this is the second case. Then this is also the same thing, that is the 293 to 1255, but it is occurring at constant volume, mCv dt by T. So after solving this one, you can get this one as a 0.0326 kilojoule per Kelvin. Then